Hello viewers, in today's class we are going to discuss an important problem from continuity and differentiability, right? So here we have a function f of x which is defined as x square whenever x is less than or equal to 1, and f of x is equal to 1 over x whenever x is greater than 1, right? So here what we have to do is to test the continuity and the differentiability of this function at x is equal to 1, right? So let us start. Now viewers, we know that a function is said to be continuous if the left hand limit and right hand limit they both exist at the particular point or the given point, and both these limits exist and finite, and moreover these two limits should be equal, right? And when the left hand limit is equal to right hand limit, we say that the limit of the function exists at the given point, and here the point is given as x is equal to 1, right? And for the function to be continuous, these two limits should be finite and equal, and these two limits should be equal to the value of the function at the given point, and here the point is x is equal to 1, right? So here what we will do, we'll find left hand limit, right hand limit, and f of 1, and we'll prove that or we'll see that whether these three quantities are equal, right? So now the left hand limit is given by a limit x tends to 1 minus this symbol is for the left hand limit. It implies that we are approaching towards x is equal to 1 from the left of 1, right? And here we have f of x, right? So here we have x is equal to 1, and when we calculate left hand limit, it means we are approaching from the left of x is equal to 1, right? That is from all values of x which are less than 1, right? So now here we'll put x is equal to 1 minus h. Here h is a very small quantity, but h is greater than 0. It means h is a positive quantity, right? So here this x is equal to 1 minus h, it lies somewhere here, that is very near to x is equal to 1, but to the left of x is equal to 1, right? Okay, so now here when x tends to 1, h tends to 0, right? So the left hand limit is equal to limit h tends to 0 f of here we have x is equal to 1 minus h, right? So now limit h tends to 0, and we see that for the values of x which are less than 1, the function is defined as x square. So here we'll have for x we have 1 minus h, so we have 1 minus h square, and limit h tends to 0, 1 minus h square is equal to 1 minus 0 square, that is 1 square, that is equal to 1. So here we'll take h is equal to 0, right? So the left hand limit is finite and equal to 1, right? Now let us find out the right hand limit. So the right hand limit is defined by limit x tends to 1 plus. This positive sign shows that in this case we have to approach x is equal to 1 from the right of x is equal to 1, right? And here we have f of x, and now we'll put x is equal to 1 plus h, because we are approaching towards x is equal to 1 from the right, and all these values which lies towards the right of x is equal to 1 are greater than 1, right? So our point 1 plus h, it lies somewhere here, and again h is greater than 0. It is a very small quantity, and when x tends to 1, h tends to 0, right? So now the right hand limit can be written as limit h tends to 0, and f of here for x we can write 1 plus h, and now limit h tends to 0, and here when we calculate the right hand limit, then the function f of x is defined as 1 over x, because x is greater than 1, right? So for right hand limit, all the values are greater than x is equal to 1. So here we have 1 over 1 plus h. For x we have here 1 plus h, right? So now h tends to 0, so here we have 1 over 1 plus 0, that is equal to 1 over 1, that is 1, right? So the right hand limit is also finite, and it is equal to 1, right? So now we see that the left hand limit is equal to right hand limit, and both are equal to 1, and now we have to find f of 1. So the function is defined as fx is equal to x square when x is equal to 1, right? So here f of 1 is equal to 1 square, that is equal to 1. So we see that f of 1 is also equal to 1, right? So now this function fulfills all the criteria for a function to be continuous, right? So the left hand limit and right hand limit both exist, they are finite, and both these limits are equal to the value of the function at x is equal to 1. So therefore we claim that f of x is continuous at x is equal to 1, right? So this is the first part of this problem, where we have proved that the function is continuous at x is equal to 1. Now let us take the differentiability of this function at x is equal to 1. Now let us test the differentiability of this function f of x at x is equal to 1. Now we know that a function f of x is said to be differentiable if the left hand derivative and right hand derivative both exist, and they are finite and also equal at the given point, and here the point is x is equal to 1, right? So now the left hand derivative is defined as limit h tends to 0 f of here the point is x is equal to 1, so we can write here x minus h minus f of x divided by minus h. So this is the definition of left hand derivative. So we have to evaluate this limit at x is equal to 1, right? So now this is limit h tends to 0 f of 1 minus h, because x is equal to 1, and here we have f of 1 divided by minus h, right? Now see here we have f of 1 minus h, and we are calculating the left hand derivative. It means we are approaching towards 1 from the left of x is equal to 1. So we'll take f of x is equal to x square. So f of 1 minus h is written as here 1 minus h square, because x is 1 minus h, and here f of 1 can be written as 1 square divided by minus h, right? So now this is limit h tends to 0. Here we have 1 plus h square minus 2h minus 1 over minus h, and this is limit h tends to 0, and this one get cancelled, and we have h square minus 2h over minus h, and we can write limit h tends to 0. We can take h common, so we have h minus 2 divided by minus h, and h get cancelled, and we have limit h tends to 0, and we can write it as 2 minus h. We can take this negative sign to the numerator, right? Now h is 0, so we have 2 minus 0, that is 2, right? So the left hand derivative is equal to 2, right? Now we have to find the right hand derivative. Now the right hand derivative is defined as limit h tends to 0 f of x plus h minus f of x divided by h, right? So this is the definition of right hand derivative. So here x is equal to 1, so we have limit h tends to 0 f of 1 plus h minus f of 1 over h, right? Now here we are calculating the right hand derivative. It means this point x is equal to 1, so we are approaching from the right of x is equal to 1, and for this we have x greater than 1, so the function is defined as f of x is equal to 1 over x, right? Whenever x is greater than 1, right? So here we have limit h tends to 0, and f of 1 plus h can be obtained from this function. So we have 1 over 1 plus h minus f of 1, so we have 1 over 1 divided by h, right? So now this is limit h tends to 0, and here we have 1 minus 1 plus h, simplifying it, and in the denominator we have h and 1 plus h, right? So now this is limit h tends to 0. We have to simplify it, so 1 minus 1 is 0, so we have minus h over h, 1 plus h, h and h get cancelled, limit h tends to 0 minus 1 over 1 plus h. So now h is 0, so here we have minus 1 over 1 plus 0, that is minus 1, right? So now here we see that the right hand derivative is equal to minus 1, right? So now from this discussion we arrived at the conclusion that the left hand derivative is 2 and the right hand derivative is minus 1, right? Although both the left hand derivative and right hand derivative exist and they are finite, but they are not equal, right? So left hand derivative is not equal to right hand derivative at x is equal to 1. It means 2 is not equal to minus 1. So we claim that this function f of x is not differentiable. It is not differentiable at x is equal to 1, right? So viewers, we conclude that this function is continuous at x is equal to 1. but it is not differentiable at x is equal to 1.